Okay.
Yes, hello everyone. Welcome to the 114th Geoscience and Geoenergy webinar today, 1st of June 2023. Today we have the pleasure and honor to host our dear friend and colleague, Femke Vossepoel from TU Delft. Femke is Associate Professor at the Department of Geoscience and Engineering, the same department as Sebastian and I work. And actually we are about 10 meters away. So we are all actually working from office today. So it's a little bit strange that we are all in the same area, but broadcasting to outside of this campus. Femke leads a research group in data assimilation for geosciences. The group's projects involve the use of geodetic and geophysical observations for estimating ground motion, such as subsidence due to gas or groundwater extraction, the estimation and forecasting of earthquakes, and the assessment of slope stability. With a PhD in aerospace engineering from the same university as she works now, Delft University of Technology, she developed her data assimilation research in the field of physical oceanography. In 2007, she exchanged the oceans for the subsurface and joined a multinational energy company for some years. Then, since her return to TU Delft in 2016, she develops data assimilation methods for a variety of Earth systems. In 2022, she co-authored an open access textbook on data assimilation fundamentals. Femke is chair of the section Reservoir Engineering, and this is the section I work at, of the Department Geoscience and Engineering. In addition, she's my boss in a way. So, in addition, that's what I meant. In addition, she is a member of the management team of the Delft Safety and Security Institute. Participating in 2 expert committees, she advises the Ministry of Economic Affairs and Climate Policy of the Netherlands on the risk of ground motion and induced seismicity. She coordinates the TU Delft contribution to the EU program called Destination Earth, an EU program to build a digital twin of the Earth. It's a pleasure and honor to have you, Femke, today with us. It's great. After some years of this geoscience, geoenergy webinars, we could hold you to give a webinar today. Thank you very much for graciously accepting to give this talk. We are very much looking forward to hearing your lecture. To the audience, please note, Femke's lecture would last for about half an hour, followed by questions, discussions. Like always, text your questions anytime you feel appropriate on the chat box, and Sebastian will take them after the lecture for you. And Femke would also welcome a lot of questions, and please do not hesitate to ask any questions that might come to your mind, especially when you text your question. It will motivate others to also engage and ask questions. So without any further ado, Femke, we are all looking forward to hearing your lecture, and thanks once more.
Yeah, thank you very much, Hadi, for this very kind introduction, and it's really a pleasure to be in your seminar. I feel honored to have the chance to do so. I remember very vividly the COVID times where we would not sit in this location but would attend the seminars at home. And it's great that we are still continuing this seminar, even though we're no longer isolated in our private homes. Today I will talk about the estimation of ground motion using ensemble data assimilation. And so in my talk I will address both ground motion, what's causing it, and how we approach it in the context of the DeepNL research program. I realize a number of speakers have been before me talking about the DeepNL program, but for those who haven't heard those talks, it's a program to stimulate research to the deeper subsurface and study the effects of our use of the subsurface on the surface. And of course, the work that I'll show is not work I do alone. I work with a team, and I'll be highlighting the work of 4 of my PhD candidates who are shown in the pictures below. They're Samantha Kim, Céline Marseman, Hamed Diab Montero, and Arundhati Banerjee. And without further spending time on this slide, I'd like to start with the 2 elements that I'll be discussing. And the first element is subsidence. The second will be earthquakes, because those are the features that we encounter here in the Netherlands, as you see in the right, but that also play a role worldwide. And on the left, you see how subsidence affects low-lying cities. This is a picture from Bangkok, but also cities like Jakarta and other cities in low-lying deltas are very much affected by subsidence. So it's important to understand the mechanisms and, if possible, to forecast how subsidence will evolve and to take measures and mitigations against it, both at the short term when it happens in terms of how do you call that, emergency response, but also in the long run, how can we mitigate and avoid that this happens? And here, closer to home, we see that subsidence plays a role, especially with infrastructure, that as the land subsides, also things like bridges will be lower, which affects, of course, the traffic on waterways. And this is just one example of how subsidence causes affects our daily life, and affects also causes a lot of damage. The damage is perhaps even more disastrous if we think about earthquakes, the second topic of my seminar today. And shown on the right is the devastating result of the 2011 Tohoku earthquake, which is actually the subject of one of the studies that I'll present today, which cost society around 200 billion euros. And similar, well, perhaps a little bit lower, but equally devastating was the Turkey earthquake earlier this year. And now in the Netherlands, closer to home, the cost of damage is a little bit more modest, but still the consequences are quite severe. And this was actually the reason for the Dutch government to also invest in this DeepNL research program that part of this research is funded by. So that gives you the context of our work. And before I dive into the contents, I'll give you an overview of what I'll be talking about. So a little bit more on the introduction will follow in a minute, and then I'll continue with a study of subsidence, and I'll highlight how the assimilation of subsidence data, subsidence observations, actually causes challenges in data assimilation. And data assimilation, I will also introduce it in a moment, is a combination of data and numerical models. In the third part of my talk, I'll move to earthquakes, specifically to the interseismic deformation. That's the deformation between seismic events where the Earth is in a way recovering from the earthquake. And we are studying that with GPS measurements for the Tohoku earthquake. Then I'll move to induced seismicity, where we're trying to estimate and forecast cyclic seismic events with models of varying complexity, and I'll end with some conclusions. But first, a bit more about the context, and specifically the context in Groningen. And forgive me if I repeat what other speakers in this seminar series have explained. I recall a very nice seminar of Annemarie Muntendam-Bos, who gave a good overview of this. In the gas field of Groningen, which you see here in the north of the Netherlands, gas is being extracted from this field, and that leads to a pressure decrease in the reservoir. The pressure decrease then induces a change in stress, and that can cause all kinds of effects, subsidence and earthquakes being the most noticeable. Now, we all know that pressure is being measured in wells, but the distribution of the pressures may vary across the reservoir, as we have faults, and they may be sealing or non-sealing, and we have different lithophases, so the distribution of the stress can be very different. And that could also mean that the subsidence has a certain character. Moreover, subsidence is caused by compaction at different levels, not only at the reservoir, but also due to ground extraction or peat oxidation at shallower levels. So we need, when we measure subsidence, we need to disentangle the different contributions to subsidence. And then the induced seismicity that's happening at the faults is also very difficult to monitor, let alone predict, because we have very limited observation at the actual fault. We only have indirect observations at the surface, and we need from those indirect observations to estimate the stress, and with that, hopefully improve our models through which we can then better forecast when we expect to have induced seismicity and when not. All in all, we have quite some information, especially from satellites. And I mention here INSAR, which I'll explain in a moment. But we have quite limited subsurface observation. It poses a challenge when you want to combine those observations into an interpretation and also include numerical models in that. And there are no direct observations of shear stress at the fault. So that's one of the main challenges that we face. So in order to address these data sparsity issues, we would really like to use all prior knowledge that we have. And the prior knowledge typically comes from numerical models. The way to combine those two is using a technique that comes from numerical weather forecasting and is known as data assimilation. I already mentioned data assimilation is combining numerical models with observations. And I'm illustrating this with a bit of an iconic cartoon that's typically being used to explain how we use data assimilation in weather forecasting. Now imagine we run the weather, we estimate, let's say, the temperature for the weather tomorrow, and what we then obtain is this green line. It's a model prediction. Now suppose we have an observation tomorrow and we measure that the temperature is lower than what was predicted. We then know that both the model has errors and the data have errors. So in order to know what the weather really is, what the true weather is like, we make a weighted average of those two. And we don't do that by adding them up and splitting them in two, but we do this by taking into account in a robust mathematical manner the uncertainties of both. And once we have found that condition, we can use that to forecast to another moment in time, and then we can do the same trick again. And by doing so sequentially, we sequentially update the model with the hope that by that the model will improve and we can have better predictions going, or better forecasts going over time. The same technique is also being used in the oil and gas industry, or in storage, or in geothermal, and then it's known as history matching. And history matching can be done in different ways, just by turning the knobs and changing a permeability field in a reservoir, but also by more carefully weighing the data and the model in a data assimilation way. And that's also how we have been using it for the estimates of ground motion. Now, I promised you to start with subsidence. So let's see what we have as ingredients for this subsidence data assimilation. The most important source of information, as I said before, comes from satellites, and we're using their INSAR, interferometric synthetic aperture radar. The INSAR data are based on a difference in phase between a radar that makes essentially radar images of the surface, and how that image changes over time gives us information on the downward motion. By, I hope you can see my mouse, but by looking at that phase difference, we can make maps like this, where you see this phase difference portrait in the colors, different colors for every phase. And that can then be interpreted to an estimate of downward motion, or northward motion and eastward motion, since the satellite has a certain angle with respect to the surface. So, by the way, this is an observation from the Japan Aerospace Exploration Agency, where they had one of the first images of the Turkey earthquake. So it's also used at the moment of earthquake occurrences, but we here use it typically for subsidence in Groningen. That is the data part, but in addition to that, we have the model part where we're using simulations of reservoir compaction, and we approach that with very conceptual idea of a nucleus of strain, which is essentially a compacting source in the subsurface. So in the case of a compacting reservoir, it would be a compacting source at around 3 kilometers depth. And by using a description of the response at the surface, we can then model the effect of that compacting reservoir on the surface motion. So zooming a little bit in on that problem, you see here a reservoir, subsurface reservoir, and we refer to the compaction as deep compaction, as opposed to shallow compaction happening more in the shallower layers. And you see that the subsidence can have quite complicated shapes, but typically it's a gradual shape, which means that if you have 2 adjacent observations, they can be, the field that they observe is quite correlated. So there are all kinds of correlations in the observations of that field. Now, moving on to the observations, there are actually there are many observations here, and that's illustrated here with the difference if we go from leveling data to INSAR data. You see that leveling was really available in certain patterns with leveling campaigns. These are these classical tripod measurement campaigns that you sometimes see in the street. And the temporal resolution was typically every 5 years or something like that, sometimes a little bit more frequent. But now with satellite data, with these INSAR data, we have many, many more data points, and these are just isolated scatterers that have been selected. So it's not even the total amount of data. And we see that the resolution over time is very high. So in the data assimilation, one of the challenges is to deal with this high temporal frequency. The model that we're using is, as I said before, quite conceptual. It's, this is the function, and I'm not going to explain all the letters, but the key element here is the pressure difference. So if we have a reservoir that compacts, the pressure changes, and we have a compaction coefficient, we have the Poisson ratio, and the depth at which this pressure difference takes place will also affect the vertical motion here indicated with UZ. So if we know that pressure difference, we can actually estimate the response at the surface. And if it's a single source, the response is very straightforward, a very nice smooth bowl. Now, in order to model the more complex geometry of a subsurface reservoir, we want to move from this very elementary bowl to something more complex. And we're doing that by gradually adding more sources here. So you see, we started a test with 1 source, then moving to 2, to 4, to 25, etc. And in the slides that follow, I will refer to this multi-strain element as a multi-component model. So I'm now going to contrast, in order to explain you something about the data simulation results. I'm going to contrast on one hand a single source or a one component model, where I'm going to assume that whatever happens above the reservoir is only due to what happens immediately below. And I'm going to talk about a multi-component model, where actually what happens here also affects the neighboring cells. And this is, as you have understood from the previous explanation, this is what we'll have in reality. But I'm contrasting the data simulation with a model like that with the data simulation if we would not have those spatial correlations. But first, a bit about the data simulation methodology. I've explained the main concept with that slide in which I showed the weather, but I also said that there was some math behind it. And those of you who have followed courses in statistics will recognize here Bayes' theorem, which essentially tells you that the probability of a state, so the probability of a certain subsidence, given our observations of subsidence, is proportional to what is here in the denominator, the probability of the observation given the state, or that's known as the likelihood of the observations, times our prior model, so our prior estimate of subsidence multiplied by the likelihood of an observation giving the same value. And there we can relate the let's say the predicted model by an operator H, which is the observation operator, times the state. So if we would take the state, not just the deformation itself, but also extend it with the pressure, then the observed subsidence is actually a function of that pressure decline plus some error, because we always have errors in observing. We also have errors in how we simulate, the so-called representation error. And in this equation, we have x, the model state, so that's the collection of all variables that change over time. And I'd like to discriminate here model states and model parameters, where model states remain constant in time, and model parameters are typically assumed to be constant. So in a reservoir model, that would be, for example, permeability, compaction coefficients, porosity. And of course, I realize that those parameters are never completely constant, but we assume them to be constant. At least they vary at a much slower rate than the state variables in your model. Now, I said before, what you use, if you read just the equivalence here of the posterior on the left-hand side with what is in the denominator on the right-hand side, and you regard the denominator as a normalization term, then you can state that the posterior is equivalent to the likelihood times the prior. So the posterior is equivalent to some kind of weight function times our prior estimate, if we can sample from that prior distribution. And that's what we do here in the particle method. So the method we're going to use in this experiment is the particle method, which seems like a very straightforward, intuitive method. Think about it this way, that if you want to know what is the weather tomorrow, you just create many different realizations of the weather tomorrow. And then if the temperature is very close to the observed, you give it a high weight. And if it's far away, you give it a lower weight. Well, if it's just one single value, one single state element that you're estimating, then this would look very simple. You would just have a Gaussian. Now imagine you are estimating not just the temperature here in Delft, but also the temperature in Groningen, and it becomes a little more complex, and you will have to, you can have a simulation that hits the right temperature here in Delft, but not in Groningen, and it will still get a low weight then, because it doesn't match both values. So the more values you try to estimate, you can imagine that this 2, 3, 4, 5, 6, 7 dimensional shape will become more and more complex. So if we look at this distribution of weights just from one axis, you can see that there are many points filling this distribution. Now, you can also imagine that as we increase the number of unknowns, if we try to estimate more and more variables or more and more parameters in our so-called control vector, then at some point, the number of samples that we have will not be sufficient to fully sample that distribution. And that is what we call weight collapse. And that's actually illustrated here for a case where we are estimating 100 variables. So for you to take away from this and to help you understand my next slides, if we have a large number of state variables to estimate, then we need a large number of particles or realizations to correctly sample that posterior distribution. And Samantha Kim has worked on this, and she started with the work that has been done by Chris Snyder of NCAR in Boulder. And what he did is he started with a very simple system of IID samples, so independent samples, and he derived a relationship for that size of the ensemble, or the number of particles needed for a particle method, as a function of the number of states that you want to estimate. And he came up with this graph, which is just a copy from this paper. And Samantha tried to copy that behavior with the one component model that I showed you before, the model where we have one single source in the subsurface, and the subsidence on top of that is only influenced by what is compacting at the deeper point. And the result that she got was a very nice correspondence to what Chris Snyder obtained. So we could safely say that the one component model behaves like an IID sample. Now, when we have the multi-component model, and you could already guess that from what I've shown before, that relationship no longer holds. So this is where she came up with the innovative idea of using theory from information theory, and we're now using mutual information to actually establish or evaluate the efficiency of the data assimilation methods. And you can then think of the information content in the prior as the entropy in the prior, the information content of your observation as the entropy of the observations. And then just as we were multiplying the prior distribution with the likelihood, we're now merging those two, or looking at the intersection of the two conditional entropies in order to determine the information content that you obtain when you combine the data and the model. And I realize this is a bit mathy, this slide. I promise you this is the last mathematical slide, but we can actually compute that mutual information, and we can use that to evaluate the efficiency of our data assimilation. And we use two indicators for that. One is the data assimilation efficiency, here illustrated as the ratio between the a posteriori analysis, the information of the a posteriori analysis divided by the prior information content. And we can use what we call the information difference, which is the information gain if you move from the prior, so from the model only, to the posterior. That's the analysis, the combination of model and data. So it's this information difference and data assimilation efficiency that we can now use to establish how large our ensemble or our number of particles has to be in order to correctly sample that distribution, the posterior distribution. And then Samantha found out that for one component model, and you have 50 strain elements, 50 sources of compaction, you actually need more than 1,000 particles, or an ensemble size of 1,000. And if you move to a multi-component model, so if you take into account those correlations, you need to go to 10 to the 9th. And if you really want to gain some information from the data assimilation, then those numbers are even higher. So in essence, the conclusion here of the work is that if you want to use a particle method for something like subsidence estimation with 50 grid blocks, then you need a huge ensemble. And that could be a reason to not use the particle method, but use another method, or to adapt, and that's what Samantha did, to adapt the particle method into a way where you actually cleverly make use of the information contained in the data. So far for the subsidence work, and I'd now like to shift our attention to earthquakes. And I'll start by showing you some observations of this very devastating Tohoku earthquake, but not before I've explained to you the seismic cycle. So shown here is a cartoon that illustrates how a seismic event happens and how then that fault heals, as it's being called in seismology, and how it gets ready for the next seismic event. So we define a number of phases there. First, the let's say this little blue phase here is called the nucleation, and that's the moment where the stresses exceed a certain threshold, and a pre-existing fault will start sliding. Now, if that sliding is seismic, then it will cause seismic waves, and those are sensed at the surface as an earthquake. And that actual moment of slipping, whether it's seismic and causes an earthquake, or whether it's more gradual and causes some more gradual movements, that's called the co-seismic phase, and that's in orange here. Now, shortly after that co-seismic phase, we'll have a post-seismic phase where the subsurface is kind of recovering from this event. And then there is let's say, healing phase of interseismic deformation. And interseismic deformation is quite a gradual deformation, which is almost linear in its behavior, and therefore the easiest phase of a seismic cycle to start with estimating that from surface observations. And in the Tohoku earthquake, we use GPS or GNSS observations of those movements in the subsurface. And you may not recognize it that easily, but what I'm showing you here is the island of Japan, where you see the deformation mostly in northwestern direction. So you see this is one single station gives these observations. So it's moving to the north. It's moving negatively in eastern direction, so to the west. And in terms of vertical deformation, we see some cyclic, some seasonal variations, but it's typically moving downward at this side of the island. Now, this is the actual fault where the epicenter was present. And we can model this pattern of deformation with a so-called flexure pattern, which you see here, where we have downward movements on the right and upward movements on the left if we move away westward from the trench. So this is 200 kilometers from that trench, and then if you move westward, you see some downward motion and some upward motion. And this pattern of deformation can be modeled with a very conceptual model, again, with Green's functions that describes this ground deformation. And that's shown here. And this is the work of Celine Marsman, together with Rob Govers and myself. And she has been estimating in these Green's function of that deformation the location of two loads. So she's assuming that there's a plate that deforms under the load of two source loads. And not only the location, but also the amplitude of that load. And at the same time, she assumed that the thickness of the plate was not very well known. So that's another variable to estimate, both on the left side of the domain as well as on the right side of the domain. Now, in data simulation, it's quite common to do an identical twin experiment. And that's where you have a model representing something. And from that model, you generate data, you add some noise on the data, and then you assimilate those data into the model just to test how the data simulation is performing. It's in geophysics, it's known as what's the name again? I forgot. It will come back to me later. But so you're doing an ideal test experiment. But what Celine wanted to do here is to do a non-identical twin experiment. So she's taking observations from a different and actually more refined and elaborate model than the model in which she's assimilating it. And that's what she's been showing here. So she has a more complex two-layer model with an elastic slab and a viscoelastic oceanic mantle, and there's a lot more going on. But she's creating deformation data from that model and then assimilating that in the other model. And doing that, I'm only showing the highlight here. The details can be found in her paper that is very close to being, or hopefully being accepted. It's in second revision now, and she demonstrates how even if you have very different priors, so very different starting conditions of your of the thickness of the plate and the locations of your load and the amplitude of the load, the particle method that she uses is able to reconstruct the actual thickness and positions and the loads of the data. Now, Celine has also done this with the actual data and still using the conceptual model. And there she found there were some complications. So for that reason, she's now moving from this very conceptual model to a more elaborate model. But I'd like to move on to the third study that I'd like to describe in this work. I see I need to hurry up in terms of time, and that's the work of Hamed Diab Montero, who's really looking at this co-seismic phase. Now, Hamed has based his work on the work on his co-supervisor Ilona van Dinter, who in 2019, with a lab setup of seismic earthquakes, demonstrated that data simulation can really help to improve the forecastability of a seismic cycle model. And she illustrated that here in this graph, where if you would have a random generator, then we would predict earthquakes at a random frequency, and the failure to predict would be inversely proportional to the alarm duration. Now you can interpret this diagram, a Multian diagram, by saying if we sound an alarm every day, then the alarm duration would be 1. We don't want to sound an alarm every day, so the goal is really to be close to the origin. And of course, we want to be successful in predicting. So if our model shows a behavior at the origin for forecasting, then that's ideal. Now, I said before, the random alarm generator would have this diagonal line. A periodic model that we see an example of here would give this red dotted line, which is hardly better, but with data assimilation, we can really push that towards the ideal goal. Now, this was the work of Ilona, and Hamed has copied that with a more complex model of seismic cycles. This is a workflow. I'll not go into detail in view of time, but where he's actually estimated shear stress, velocity, and state using an identical twin approach. And he's doing that with the Garnet seismothermomechanical model, which is coupled to a data assimilation system known as PDAF, developed in Bremerhaven. And now, mind you, that he has been estimating the stress variables, or the state variables, not the parameters of the seismic cycle model. And he has focused on two types of events, shown here the shear stress at the observation location, and he has slow slip events and earthquakes. And I'm moving a little bit quickly here, but the key outcome of his work is that for this co-seismic phase, where we have a sudden shear stress drop, shown here by this almost vertical evolution of shear stress, we can have, for a slow slip event, we see quite a good distribution of our posterior samples. And also for the interseismic phase, this is the case. However, if we move to an earthquake event, we see that at the time of the earthquake, some of the ensemble members, and in this case it was done with an ensemble common filter, have already slipped, but some are still at a high shear stress level. And if you then take the average of the ensemble, or the ensemble mean, you end up somewhere in between, which is probably not the best representation. For the interseismic phase, he gets nice results and the method works well. Now, because of this bimodal structure, Hamed is now looking into non-Gaussian methods where we are able to deal with nonlinearities in a much better fashion. And just very quickly, his end result is that also with this system, he really improves the forecastability of the method. So the colored lines here for different evaluations of the data assimilation results. Hamed has published this in a very recent publication, which you can find online. And he's now working on actually realistic data assimilation using the data of an experimental setup in Japan, where two blocks are sliding on top of each other, and we have different regimes of seismic events. Very quickly, two slides of the work of Arundhati-Banerjee. Arundhati has done similar experiments as Hamed, but then using a particle filter instead of an ensemble common filter. And she looked at the importance of updating parameters. And she could successfully show that if you update both the state and the parameters of the model, you get better results in this co-seismic phase than when you would just update the state, as is done in many other studies. So this is where I'd like to end, and sorry, Sebastian, Heidi, for running dramatically over time. But I hope to have shown to you how we can use in-SAR data assimilation for subsidence estimation, and how correlations in the field actually complicate the use of simple methods like the particle filter. I've shown you that the particle method is effective in simulating interseismic deformation, at least in a non-identical twin experiment. And I've shown you how data simulation can effectively improve the simulation and forecasting scales of earthquakes in seismic cycle models. Now, this work is not standing alone. We're also looking at the separation of deep and shallow signals in subsidence. We're looking at, as I mentioned before, at Gaussian versus non-Gaussian assumptions in data simulation for seismic cycle estimation. And I just squeezed in a little picture of Jenny Soontarn Rangsang's work, very exciting, where we're looking at groundwater extraction and how that affects subsidence. And I also want to mention the work of Gabriel Zebra, who joined us to look at heave estimation in a case of CO2 storage. So there are many different applications possible. And with a big thank you to my team, I'd like to conclude this seminar.
Thank you very much, Femke. That was absolutely fascinating. Plenty studies and many people involved. We have plenty questions posted. We have to stop sharp 5, so we have 15 minutes for discussion. Sebastian, please.
Yes, thank you very much also, Femke, from my side. It was a really nice presentation, and always great to see learn more what your colleagues who literally sit 2 doors down the road, down the corridor, are doing. Yeah, lots of questions, and from many names that will probably be familiar with you, and they largely fall into two categories. I'm trying to group them a little bit. So we have one from Tejas and one from Herminio, and I'm going to put them all together because they touch upon the same, very similar issues. So Tejas asks, what is the length scale that determines the correlation in subsidence? And Herminio sort of, I guess, asked the question in a slightly different way. It says, thank you for the very nice presentation. Can you please clarify the state of the art is for multi-resolution data assimilation? Because geoscience data is provided at multiple resolutions. Near wellbore, we have good resolutions, away from the well, poorest resolutions, we have multiple scale dependency within the data. So how do you deal with the multi-scale nature of our data?
Oh, and then to answer this in a short amount of time, that will be challenging. So the first, can you remind me, the first question was...
what is the length scale that determines correlation?
Of course, we later go into this multi-scale, yeah. So Theos, the length scale of the signal of subsidence is very much determined by the depth of your source. So the shallower, the shorter the length scales, and that's also why if we try to assimilate data for the shallow compaction, we use much narrower or even uncorrelated data points. But in the deeper you go, the broader it becomes, and then it's typically tens of kilometers correlation in the case of Groningen. And then the multi-scale, that was Herminio, I think. Very clever question, Herminio, and yeah, that's quite challenging, because actually what happens is you get a disbalance between the highly accurate, highly frequent, densely sampled in-well data and the more broadly distributed data throughout the surface. And we can play with the error covariances. That's a technical answer. So you can attribute different weights to the data, and you can make sure they're in balance. But ideally, you would want to have a more even distribution of the data. But the answer in terms of data simulation techniques is really to tweak with the to model the error covariances in an appropriate way.
Okay, thank you very much. There's a follow-up question that I have, but I'm going to keep that and give the, for the sake of time, and may ask it at the end or over coffee in one of the coming days. There's another set of questions that go more into the geomechanics and the rheology, and again, I'm trying to group them a little bit. So Wilhelmin says, hi Femke, thank you for the very nice presentation. How complex can the mechanics constitutive models be if one needs to match real compaction data? So plastic deformation also play a role in subsidence and uplift, but they're nonlinear, scale dependent. So we have the scale issue again. What's the right way to assimilate data considering nonlinear mechanics?
Yeah, Willemijn, again, very clever question. They must have a good supervisor.
I don't know who that is.
And yeah, so at the moment, if you look at more operational studies, then typically people use the Geertsma approach, which is actually the integral over elements of strain in a disk setting. So it's of similar complexity as the elements of strain, I would say, but that's only elastic compaction, so only the elastic response. At the moment, the work of Samantha focuses on separating the shallow and the deep. And there we limit ourselves to the elastic component because that's the largest and the most noticeable response. But you're very right in observing that there's also a plastic response. And this becomes much more important when there's, for example, more clay. That's something that Jenny is now also facing in her work in Bangkok, where we really have a delay in the response. And of course, the more accurately you want to model those nonlinear behaviors, the more complex the models get. And well, for the data simulation, that's you're then entering actually in more exciting research, because the nonlinear behavior poses all kinds of challenges for the data assimilation, where we can then develop new methods.
So now I need to ask my questions, because I'm itching to do this.
Go ahead.
Because you mentioned the clay. So coming from a reservoir characterization, reservoir modeling point of view, there's a lot of bias in how we interpret data and how we actually model, say, distribute clay in the amount of clay in a reservoir model, not just uncertainty in the data itself, but also our personal bias, which you have in the Bayes theorem. So how do you deal with that in your data assimilation approach?
The bias of the user.
Bias of the modeler of how we interpret the data and how we deal with uncertainty in the data itself.
Yeah, the easy answer would be I would knock on the door of Sebastian Geiger and ask him. No, that's complex. So, but that's perhaps an important thing to mention, is that, you know, as a data assimilation developer of methods, you would always go back to the source and ask the expert on your assumptions on how to model the uncertainties. So if I have a reservoir permeability or transmissibility that's uncertain, I would like to go back to the geologist who built that model and discuss with him or her, you know, how would you, what uncertainties would you ascribe to different parameters, and then go from there. And that's what I sometimes refer to as the art of data assimilation, because even though we claim to have robust mathematical methods to do the data assimilation, there's always a human factor. So that's also why I asked you the question, like how do we deal with human bias, because that's also there in the way we deal with problems. But we try to formalize the biases as much as possible in a mathematical formulation, and from there apply the math rigorously, so you come up with, you know, the most objective answer possible.
Because we have looked at, and then I shut up, because we looked in the past at situations where just you follow different workflows that are all approved, and different companies use different workflows, and you come up with very different reservoir models. And so just because you follow standard workflow A, and you believe that's the best one, that can lead for the same data to a very different model than standard workflow B, and then you can argue until the cows come home which workflow is better. But you have two models.
No, and thank you for making this comment, because that allows me to talk about benchmarks in data assimilation. And I find that in assisted history matching, so in the oil and gas industry, we've defined a number of good benchmark studies where different data assimilation techniques could be compared with different data assimilation workflows, I should say. But these are not present in all fields. And in DeepML, we're also talking about, can we somehow benchmark our seismic models, because and seismic data simulation or estimation inversion techniques, because that would really help us to assess a bit better how the performance really is.
Yeah. Okay, now back to our audience. So I'm going to take two more questions here. Again, they're related. So Gabriel says, thank you for the great presentation. I have two questions. How does noise in the measure? I'm just going to take one of them, because there's a very interesting follow-up question from someone else. So how does noise in the measurement impact the information content, which then impact the amount of particles that we would need?
Yeah, that's a good question. Noise is not affecting the number of particles as such, but it will affect how in the end the data influences the end result. So the number of particles that we need is very much determined by how well can we sample the distribution. It doesn't say whether the distribution is broad or narrow, and the uncertainty in your data speaks about the width of that distribution, but that's more of a relative sign. Of course, if the data are very noisy, then they will likely not provide any information to your system at all. But we found, especially in the seismic cycle experiments, that suppose you have stress observations and they're of very low quality, then still they provide significant information on that behavior, and it's worth assimilating them. So even noisy data can be used in a very valuable manner.
Thank you. And then the last, but certainly not least question, again from familiar name, David Brun, asks, if you were to use data assimilation for earthquake prediction near real time, what kind of data would be required?
Yeah, very, again, a very clever question. And that's something that we hope to address in a follow-on project of this, this seismic cycle project, where what we measure at the surface are actually seismograms and from accelerometers, and that ground motion then needs to be translated to the source mechanism of the earthquake, and then you have a moment tensor, and from that moment tensor, with some prior knowledge, you need to estimate the strain, and from the strain you estimate the stress. So you have this is this indirect translation of the surface observations to the variable of interest, and that's really complicating your interpretation, but it's also a good challenge for data simulation people to work with these highly nonlinear relationships between the observed quantity and the variable you want to estimate.
Great, thank you. And before I hand over to Hardy, just let me bring up one final comment. So if you want to learn more about,
I wanted to make an advertisement for that, but now you do it. Thank you. Yeah.
Here's the free link.
We just Googled the link and found it, so we posted it there.
Super.
So there's a free textbook, and neither Hardy nor I, we get any royalties for that advertisement.
It's a free one.
Thank you.
With that, Femke, thank you very much for a really nice presentation. Thank you to the audience for the questions. And Hardy, over.
Yes, thank you very much all. Next webinar will be on mid-June, 15th of June in the afternoon, 4 p.m. Central European time. We will host Carl Jackman, sorry. So that's why I try to bring my cache memory for his family name. So Carl will speak about the rapid reservoir modeling, RRM, that Sebastian also has half of his heart on. So we'll see how we can use this technology to actually sketch new models for reservoir. Stay tuned until next 2 weeks from now. Stay happy, healthy, and also tuned in for this geoscience webinar. Thank you very much, Femke. It was fantastic. And many people would also come. Many colleagues actually texted us that they are busy right now with this, with the exam, with that. So I'm sure they are going to catch up later. David says thank you, Femke.
And can I make one addition, because I couldn't think of the word for a twin experiment in geophysics. It's inverse crime. Isn't that a beautiful term?
It sounds like a good novel to read in the evening.
Now I know. No wonder why you forgot that name. So
it was a great pleasure being here, and thanks again.
Pleasure. All ours. No, thank you very much, Femke. I believe many students will also watch your lecture as well later. It's a video lecture, a good cause for the community as well. We will revisit this many times in the near future and longer. Thanks a lot, everyone. Stay happy until 15th of June with Carl from Imperial College London. Thanks a lot. Bye-bye.
Thank you.
Bye, everyone.
Bye.
Bye.